Okay, my idea today was to essentially do an exercise just to see if we got all the material in a sense. And the goal is to prove a theorem by Kalinin and Katok using all the material we had developed so far. Okay, so we will be very short from having almost a trivial proof, and the hope is to try to address what is difficult and why the proof is not trivial of Kalinin-Katok, and how to solve this non-triviality. So this hard part of the proof. So let me first put the setting they are working with. So this is actually a theorem that started the non-homogeneous theory. So the setting is we have rho from n minus 1 into Sn z. So you have n minus 1 commuting matrices in dimension n, and you make rho act. So you induce from there the action on the torus, and we want n to be at least 3 because we want to have at least 2 commuting matrices. With one, what I'm going to say is not true. And we want, as we did in the case of the linear action for the torus T3, we want some niceness of these matrices. So assume rho of n is diagonalizable over R with positive eigenvalues different from 1, all different. Okay, that's for every n. Actually, what we really care about this condition is the following: that Rn can be split as E1 plus En, so as n one-dimensional guys. And we have this chi I from Rn minus 1 into R. So these are n minus 1. So functionals. So okay, let me do the change. Even though this n is bold-face n and the other is, but certainly I'm the only one seeing that. So let's switch to D. Okay, now it's good. So essentially what we care about, what is written above, is a consequence of this, which is almost trivial, although one has to do one epsilon of argument in order to it to be true, but so far this is quite trivial. Rho n of B is e to the chi I n times B for every B in EI for every n in CD minus 1. And one extremely important property of these chi i's, which come from this putting there that they are different, and it's actually a little bit more than being different, but since this is SLD value, the following will be true. When I do this guy into what's the name for this guy? Let's call it L. Why not? Okay, so it's this plane where the sum is 0. This is an isomorphism. And what is important of being an isomorphism is that take any element here, whatsoever element here, then I have a t which corresponds to this guy. Now this t in Rd minus 1 can be approached by rational guys, and if I take products of this rational guy by the common denominator, this becomes an integer guy, and then I have an element of the action which, at least up to a multiplicative factor, has pretty much the Lyapunov exponents that I wanted. Okay, and this is particularly useful if I want to choose a guy where the first coordinate is positive, the second is negative, the fourth is positive, and as soon as I make sure there is one negative and one positive so that the sum can be 0, then I'm able to find the guy doing this job. In particular, I can bring one being positive and all the rest negative. I can do it. So that's the really very strong assumption, but that's our linear dynamics. Okay, and for this linear dynamics, we already proved the following theorem essentially. So this is actually Katok-Spatzier, which we prove in the case of dimension 3, but it's the very same proof, which says that if mu is rho invariant and ergodic, then either entropy of every element is 0 for every n, or mu is Lebesgue. That's actually a version of Rudolph's theorem, but instead of time 2 time 3 for these linear maps. Okay, so now the goal is to have a nonlinear version of this Katok-Spatzier. So now we consider alpha an action of Cn minus 1 on the torus Tn, but will be nonlinear. So here 1 plus epsilon will be enough. It's infinity. Really, it's not so serious. And once I have this action into diffeomorphism, this induces a map from Zn minus 1, a homomorphism, into automorphisms of the pi 1 or even the h1, whatever. These are all same guys. So, and then I went back to n. Let's go back to d. So this is CD, and hence this is actually what is called GL of DC. That's pretty much the same. It's two notation for the same object once I put the CD there. And just to make my life simple, let us assume that alpha sharp is rho is as before. Okay, so like this there. So I have an action, and the information I have on this action is exactly this, that the action on homology is as beautiful as this. So it will be some linear action. It could be identity because all the elements could be homotopic to the identity. Or it could be more complicated, and I'm really in this more complicated situation. Now comes just a simple observation, which is the following. Well, actually, this is not an observation, this is a lemma first, and then I have the observation. There exists H from TD to TD, homotopic to the identity, and Hölder continuous, and is essentially unique. So I will eventually give an explicit formula for this H. And gamma finite index subgroup such that H compose alpha n is rho n compose H for every n in this gamma. And actually, let me add here. So since I'm saying homotopic to identity, I'm assuming automatically that H is continuous, but actually it's Hölder continuous. Okay. So we have this semiconjugacy. If I restrict to this finite index subgroup, if not, I have to add a translation here. So it will conjugate to affine, not to linear. And for affine, I certainly have the very same things as here, so it's not so bad, but it's just some finite non-agreement. We have to come from some sort of torsion or finite cohomology, which we can discuss later. It's some fun, but it's some finiteness after all. So it will not affect our life, this finiteness.
This finiteness subgroup also covers the case when alpha is not necessarily orientation preserved.
Yeah, certainly I can restrict to this finite, and that's what I'm going to do. So this gamma is still isomorphic to CD minus 1 because any finite index subgroup of CD minus 1 is isomorphic to this guy. I think I did this exercise once even. I don't remember what's the complication of it, but there are some subtlety in showing this. Almost trivial. So when you build this isomorphism, it's really a triviality. Anyway, so since this is isomorphic to this, we can assume that we started already from this guy and move on. So it's not really. And again, this is just because I really don't want to write down the affine guys and don't do matrices instead of affine. But it's not more than that. Okay, so once we have this lemma, that we are going to see the proof later, it is an important lemma, even the proof and the picture of it. But we have this set, which I call M alpha lambda, which is all the measures mu, probability measure on TD, such that H star mu equals to lambda and alpha n star mu equals to mu for every n. Okay, so it's the invariant measures for the action alpha that project to Lebesgue. And since Lebesgue is invariant by the row action, by the linear action, then there is, so this set is, so it makes sense to ask this property at least. Okay? Because when I apply H star here, I will get the same as the H star here, which is lambda. Now the observation is that M alpha lambda is actually non-empty. Okay, and the reason why it is not empty, and actually the ergodic elements there are non-empty, is because we can define M lambda, which is all the mu's prova on PD, such that H star mu equals to lambda, and this guy is compact and alpha and invariant. Where the n, again, there is where I'm using that lambda is an invariant measure for rho. And then once I have compact invariance, I can average here and produce an invariant measure. And the fact that this ergodic is not a problem. Okay, I said compact and convex, because so I want to average, I need to keep the convexity, and hence this guy is now compact and convex and non-empty, and as always extremal points will be ergodic. Just, I don't know why, but they have to. So we have ergodic invariant measures for the alpha action. That projects to lambda. And then the theorem by Kalinin and Katok is that if mu is here, in there, then mu is absolutely continuous with respect to Lebesgue. And moreover, chi I for the measure mu, let me just do it in a short way like that. So this actually is saying much more than what is written. This means that this measure mu, when I apply Ocellet's theorem to this measure mu, I have a splitting into d different spaces, one-dimensional, whose Lyapunov exponents are the same as for the linear. And actually much more is true. So observe that I'm not asking the measure mu to be ergodic, and there are two reasons for not asking the measure to mu to be ergodic. First of all, because you prove it for ergodic measures, but once all ergodic measures are absolutely continuous, then all invariant measures will have to be absolutely continuous. But the second reason is an addendum that we prove with Katok, that was myself, that says that there is only one measure in there. So it is automatically ergodic. So there is only one that is absolutely continuous. And as I said, the idea is to prove this. So I will give some pictures on how was the original proof by Kalinin and Katok of some of the statements, and I will give the proof using what we developed of the same statements. So the first step in the proof is actually to establish something like this. So that's the very first step in the proof. But this, even though this is the first step, let's go to the 0th step and understand this lemma, how you have this semiconjugacy.
So lemma, I guess you don't get higher regularity.
Yeah, you never will get better. Well, yeah, so the lemma itself is very, very general. I need very little of hypothesis to get it, even though I need non-trivial hypothesis, which we will see in a second. But then after the theorem, and actually that's part of the developments in this addition and even further, already here these developments show up a little bit, is that, yeah, you get better regularity, but it's in a very weak form. So it means that, for example, you get, which is related to this fact, actually, you get that if I restrict this H to an unstable manifold, it is a C1 diffeomorphism, C1 plus Hölder diffeomorphism. Okay? But that's for restrictions to unstable. So if I just look globally, then, well, I have a lot of point of smoothness of these functions, but we don't know whether it has to be true or not that H will be smooth on an open set. So that's an open problem. Let's say, even for general guys, or even if you assume real analytic here, which will give you a little bit more of hope of having this smoothness on an open set, but even for the C1 plus epsilon, is not clear whether you can build an example where H is not smooth on an open set. So there are examples where H is not smooth everywhere. That can be done, but I probably will discuss it when we discuss examples. Okay, let's go to the lemma, because the lemma is very, very easy. The lemma is the following, so let f from the torus tt to dt, assume that you look at, let's say, f star or f sharp. I like really to, even though it doesn't make sense, I still like to do it. This is not well defined, because I should say who is the base point for talking about pi 1, but since I know it is a billion, I don't care about the base point, and this is a well-defined option. And assume, so this is a C0 map, assume this guy is hyperbolic. And for this, I just mean no eigenvalue of modulus 1. And also I want it to be invertible, so F sharp. I don't even need F sharp invertible. I want F sharp 1 to 1. Okay, it could be times 2, which is not invertible, but it's still 1 to 1. So I don't need F to be invertible. Even if F sharp were invertible, I still don't need this guy to be invertible. Yeah, I'm saying that what I'm saying is right. So we will see in the proof, but I think everything is good. In the worst of the situation, you assume F sharp invertible, and then life is even simpler. Then there exists H from TD to TD, C0, homotopic to identity, such that H compose F equals to this, let's call it A, this H, and 1 if F is Hölder, then H is Hölder. 2 if nothing, yeah, well, if H hat compose F equals to A compose H hat, and H hat is C0 homotopic to identity, then the difference between these two maps is a constant and is this constant. It's a constant belonging to this finite set. Or something like that we will see in a second. But it's a finite set. It's Hartman-Grobman did it before. And probably. So it's a lemma that appeared also in Frank's thesis that he uses in a crucial way. He does it as well for nil manifolds, which then is a little bit more complicated. So in this case, it's really Hartman-Grobman. In the case of nil manifold, you have to, it's still not Hartman-Grobman, but it's in a more elaborated way, so it's generally more complicated. It's still just a lemma in his work or proposition. So what he really does is give natural hypotheses which are, well, F being an Osov, and he put extra hypotheses that will guarantee that this is hyperbolic. So he doesn't need to put it as a hypothesis. And more important, this being injective. So he doesn't have all the optimal conditions. Then Manning put all the optimal conditions to get, which is no condition at all, to get that this is hyperbolic and that this is one-to-one. But even Manning bases in a little bit in Frank's business. But yeah, this lemma is really Hartman-Grobman. So, let's write down the proof then, since it is just Hartman-Grobman. So we write f of x. So well, we lift anyway to the universal covering. This can be done without a problem. And we get f of x being ax plus phi of x, where phi is ZD periodic. We have RD splitting as ES plus EU. And then we look to H as identity plus U, where U is CD periodic. Okay, typically Hartman-Grobman will ask only U to be bounded and continuous. We are asking it to be also CD periodic. That's the only difference between the standard Hartman-Grobman and this, and of course U continuous. And here also U continuous, F continuous. Okay. Maybe not. They go over there. Okay. Now we write the equation. The equation then is H composed F equals to AH. We write phi as phi s plus phi u as us plus u with respect to this splitting. And then this becomes f plus u compose f equals to a plus au, which is a plus phi. You cancel this with this, and you split this equation as phi s as us compose f phi u as these two equations. And then you write this guy as, there is one that is always fine, which is this guy, because this is giving us u minus au inverse u compose f equals to au inverse phi u. And this is identity minus a contracting operator equals to this. So the solution to this is sum with n larger than or equal to 0, au minus n phi. Actually, I'm having even one more because of this, phi u composed with fn. And this is uu. Now this, we have a little bit more of a problem to solve. And actually, we are going to assume here, either f invertible or as equal to 0. If not, we have problems. I think something can be done. But anyway, let me not try to do it. And then this equation becomes the same as this equation. So either it's inexistent because I'm asking it to be inexistent, or I get pretty much the same equation. Us minus as us compose f inverse equals to minus phi s compose f inverse. And I get here that us is minus sum n larger than or equal to 0, as n phi s compose f minus n minus 1. Okay, so that's essentially settles everything. Well, at least the continuity. So continuity, we get it for free. Periodicity of the solution we get because this is periodic, and composing with this, it will keep the periodicity. So this guy is as periodic, and actually, by discussing this periodicity is where you can do something even in the case that f is not fully invertible. But anyway, let's forget about it. Now, about Hölder continuity, which is more interesting than continuity, you just check. Let's do it for the UU. For the US, it's pretty much the same. So you do this minus this, and then you bound by this, let's say, norm of AU inverse is some lambda smaller than 1. Then I have here some lambda to the n. Then I have phi u compose fn at x minus phi u compose fn at y. Now the problem is that this could be very wild in principle. Then what I do is just I put the power theta here. Okay? And I fit F Hölder, and it was wrong. It's Lipschitz. Now it's right. really need Lipschitz holder is not enough, then to the power 1 minus theta. Now this guy here is just 2 times a constant c to the power 1 minus theta, where c is the supremum or the maximum norm of u. Since it is periodic, this is completely bounded, so you forget about this is a constant. And then you concentrate on here, and this is less than some. You have this constant c here, then you have some n larger than 0, lambda to the n, and then this guy becomes some Lipschitz constant of u, which is constant, and then we get L to the n theta. Actually, we had an n plus 1 here, we keep the n plus 1 here, and then this is, so L is max of Lipschitz of f and Lipschitz of phi u, which is pretty much the same number in reality. So this is L, okay, let's keep it, L to the theta times n plus 1, and we get x minus 1 to the theta. And that's it. You make your choice of theta so that this L is fixed, even though it's huge, but lambda is smaller than 1. With a theta close to 0, you bring this to 1, this is 1. So lambda times L to the theta less than 1, that's the choice of theta. So theta is whatever smaller than log lambda over log L or vice versa, something like that. And so, but what is even interesting is that you have a very explicit control on the Lipschitz constant. And then you do the same for the US. So that's it as the Lipschitz. Now, if you look here for what happens with h hat minus h, you can do it 2 ways. One is just follow the proof, and notice that h is uniquely determined. So the only non-uniqueness comes from the different choice of lift for f. Okay? So then one can just follow this analysis and solve the issue. There is a second way of doing it, which is the more classical way. So we have this guy, and this implies that h hat minus h compose f is equal to that. Now, since both h hat and h are homotopic to identity, the difference is homotopic to 0, which means it is a periodic function. So it can be lifted naturally to Rn up to some integer. So there exists a hat minus h. Let's erase here because this is useless now. So we have h hat minus h tilde from Td into Rd, which is a very well-defined object. There are not one, there are several choices, but any of the choices is the same for us. And this guy will satisfy that this composed with f minus this has to belong to Z. Because this equality down here implies that this is belonging to Z. Okay, so let's call it D, belonging to CD. But then I write this V as E minus I of W, just because, and maybe I minus A is better than A minus I. It really doesn't matter. So this is invertible on RD, so W is naturally in here. And once I have this, then I can just bring this to the other side, and I get something like H hat minus H minus W is equals to A times this. Now, A being hyperbolic, this being bounded implies that this has to be 0. And that's exactly what we said. And observation is that the cardinality this is the same as determinant of A minus I, which is the same as cardinality of the periodic point of fixed points of A. And actually, the whole point was that A has fixed point 0 typically, but A have other fixed points. And for every fixed point of A, there will be a fixed point of F, maybe more than one, but at least one. And this lift we choose here, the natural choice actually was to lift so that fixed point lift to fixed point. And actually, even if I don't make this choice, there will be always a guy which is fixing the lift. And these are the different choices I had in these liftings. One for who is going to be 0 for the lift. And that's the bisection from here to here. Even though it's not natural. Anyway. So, okay, so this settles all these business.
So, but is it obvious that U is homotopic to 0?
Yes, it's sum of guys homotopic to 0. So, if sum of periodic is periodic. So U is US plus UU. Each of these guys is periodic because UU is something like that. And this is just a matrix applied to this function, which is periodic. So this is a sum of periodic functions. It's an infinite sum. Still, if I do x plus n, then this becomes f plus ak to the n, but then phi absorbs it. Okay, now that we have the lemma, this is the main abstract lemma, then we have the corollary, of the third property. Or the last property, whatever it was. So the non-uniqueness is fully encoded here, and this is a finite set in particular. It says if G compose F as before, then and H is homotopic to identity, so it's one of the solutions there. Then H compose G is plus some constant C, and actually this constant C belongs to this guy here, and B is the seizure of the guy. So the fact that B has to be this guy is obvious essentially because if you look the action on homotopy, I put G sharp here, H is homotopic to identity, so disappears, H homotopic to identity disappears, constant disappears, so G sharp has to be equal to B. So now the proof of this, okay, is not right. So C belongs to the inverse of this. Now it is correct. And now the proof is just let H hat be the inverse, oops, compose H, compose G. So this actually is in principle only not well defined. So of course if B were invertible then I don't have any problem. But in case B is not invertible, it's still well defined because what you do to define this is take H tilde, a leaf to the universal covering, and then consider this guy. And when you do this in x plus n, you will get B inverse H tilde of Gx plus Bn. And then H tilde is homotopic to identity, so this is B inverse H tilde Gx plus Bn, and this is B inverse H tilde Gx plus n. So you get a continuous map which is homotopic to identity on the torus. So H hat is homotopic to identity, so it's a well-defined map on the torus homotopic to identity, and moreover you get very easy that H hat compose F. Okay, I forgot. Oh no, I said it. So this is compose G, compose F. This is B inverse compose H, compose F, compose G. And then this go as B inverse compose A, compose H, compose G. And this is B inverse compose A, compose B, compose H tilde, compose G. Oops, yeah, compose H tilde, okay. And this is A, because again, the same computation that I said before, saying that this is true, then here tells me that B and A commute. So H tilde does the conjugacy equation, and hence H hat here has to belong. So plus this. Which hence mean that when I apply B to both sides of the equality, I get this. Keep on. So here you get that H compose G equals to PH plus B. A minus I. And then we are done. So I'm not having that these guys commute, that this guy conjugate to linear, but it conjugates to affine. And this affine guy just belongs to this business, which is the same. Notice it is useful to notice that this is the same as this of BCD, and this is contained. And actually, most of the time it's just equal because B of CD. So if I'm assuming everyone is invertible, like we are really going to assume, you get equality here. So it's always the same set. There is no B over there. So once I know that there is really the same B everywhere, it's just a matter of taking a finite index subgroup, which is where this C vanish. Okay, so that's our last. Wow. I thought I was going to almost prove the theorem, and I just get into the lemma all the time. Sorry. Anyway, so in the general situation now, when we go back to our main lemma before, we have this alpha of n. We take any of the guys, because all these matrices will be hyperbolic. So, and even I didn't say about irrationality, it will be irrational, but they always will have one n node, so that this is hyperbolic. That's very trivial, even though it's true that for every n this will be hyperbolic. We don't need it so far. We just need to know that there is one guy. Then from this guy, I get my h. So this follows from the first lemma, h is Hölder, and for every other n, I get that h compose alpha n is rho n compose h plus some c of n, where this c of n belongs to rho of n naught minus identity inverse of c. Now this is a group, so C goes into here. And actually, I only care in this mod CD. And now C is not a homomorphism, it's a cocycle. Okay, so we can see that C of n plus m just follow from this writing plus the standard formula. This will be something like C of n plus rho C of you will get this cocycle type of formula. This just follows from putting here. So this is h compose alpha n plus m minus rho of n plus m h, because that's exactly how you define C. And then this is the same as doing h compose alpha n compose alpha m minus rho n rho m of h. And now for this guy, I get that this is the same as rho n h compose alpha m. So this is this plus C of n, because here I'm applying the formula for n, forget about alpha m, and this minus rho n rho m h, and now I take the common factor rho n, and this I get Cn plus rho of n Cn, and that's what I wrote, so I was correct. So it is a cocycle. So it's not a homomorphism, but still the kernel is a subgroup. So it's not normal, because that's what happens with cocycles. So the kernel is still a subgroup, but not normal. Not necessarily normal. Of course, here everything is abelian, so any subgroup is normal. So this is a subgroup because if this vanish and this vanish, then this vanish. Well, that's it. And it's finite index because the image of C is finite. So then it's finite index. and that's gamma. And once I'm choosing gamma b0, then the formula is true. Okay, so I'm sorry I just went to the lemma. I am to the whole business, but I hope on Wednesday to finish the theorem, Kalinin-Katok theorem. But it's good to go through this once, not only once in a life, once every couple of years. Okay, thanks. Okay, so let's state the theorem we were working on. Is Kalinin-Katok. As we have C d minus 1 acting on the torus TD. This is alpha. Alpha sharp, we call it rho. We assume is taking values here, and we showed a lemma or a couple of lemmas that implies that after taking finite index, and I'm assuming that's already happened, H is Hölder. We only care about continuity, but it is Hölder after all. Homotopic to identity. This is for every n. CD minus 1. We take mu such that H star lambda is Lebesgue. Oops, H star mu equals to lambda is Lebesgue. Mu ergodic for alpha. And the action rho is what is called a Cartan action. Which means RD as D one-dimensional spaces. And B is e to the, actually, to be Cartan, you just require this, even though I wanted it without the absolute values or without the norms, which is pretty much the same. Of course. So we have this, and the chi-i's are some functionals. So this is Bir Cartan, essentially means that. And well, actually, if you want to be Cartan, you want the chi-i's all being non-zero. So, because if I don't ask it, the identity would do it, and I want really something to be happening. Then, mu is absolutely continuous with respect to Lebesgue. That's what they prove. Okay. So the first thing we did was to establish the existence of the H so that we can state the theorem. Okay. Now, once we have this, we have all the power of all the lemmas we were proving and all the theorems we were proving before. So notice what we have at once. So we take mu, we apply, oops, I forgot about smoothness here. So we need the C1 plus alpha. Smoothness there. Guy. We take mu, we apply oscillators, and get a splitting of TTD equals to sum up to some L and actually I can even go and put the I upstairs, and these are these coarse Lyapunov spaces. And we have this chi I mu of n, which I can use as a definition of this chi iu of n without much of a problem. It will be equivalent to all the other definitions we have discussed as the integral of log of the determinant of the alpha n restricted to this EIA of x d mu of x. And this is a functional, actually extends to Rd minus 1 as a functional. Now, the following lemma is a corollary of our discussion, but I will give two proofs. Is for every I from 1 up to d, there exists a j such that, and t sub I, and a positive number such that chi I is c sub I chi. So each coarse from the linear, but for the linear the coarse are the same as the non, even though I didn't say that is a consequence of this. Each coarse is proportional to some guy above. And since all of these guys are non-proportional to each other, this means in particular that these guys are non-proportional to each other, which means that I need to have L equals to D. Because I need D non-proportional guys, each one contributing at least dimension 1, so I cannot have more. These guys have to be 1 dimensions, and this has to be D. So it's a corollary. L equals to D, dimension of EI x equals to 1. So you see how powerful is this very sort of naive type of property that automatically give me a lot of counting properties. Now proof of lemma, let's call it lemma 1. Proof of lemma 1. And as I said, I will give two proof of that. One is much more geometric, which is what is given by Kalinin-Katok, and the other is what we have discussed before. So let's do first the one we have discussed before. So we have this map H, which conjugate these two dynamics here. Okay, and we can apply to this dynamics this property that we saw when we apply the dynamics above. So we take alpha, we take W chi I mu, n equals upstairs, and we saw that this is less than or equal, and actually it is equal, because when I sum I get equality, but again, the only thing we care is the inequality here to H rho n, here is mu, here is lambda, and now I put the same coarse here plus the fiber. Given the fiber. Okay, so I can do this both for these chi i's mu, as well as I can do for the chi i's coming from the other. Okay. Now, now let's do the argument. Just 1 second. So I want to claim that this guy is non-trivial. Actually, I need the other inequality as well. Wait a second. Okay, so actually I want this, but for these chi i's. Which is pretty much the same. So not for the coarse of the guy upstairs, but for the coarse downstairs. Okay, where this could be empty, there is no problem, and I need equality. Probably I can do it otherwise. Okay, once I have this, the equality I get by summing. So remember that whenever I get the inequality, then I sum over everyone and apply the standard rocking, and I gain the equality. Okay, so once I have this, imagine that this was empty. So if this were 0, then I have 0 contribution here, while this guy is chi I of n, and this guy doesn't matter. Actually, it has to be 0 because that guy there is 0. But then I get 0, 0, and a chi I n of n there. So this is impossible.
So I'm kind of getting confused about it. So why isn't the first W chi I B?
I can choose what to put here. So I define W chi, whatever, actually let's call it even eta, so give me any functional whatsoever, and I can define this as the intersection of W, U, n, assuming that eta of n is positive.
I see.
I don't need to be eta to be a coarse exponent or anything to give this definition. And tangent to the tangent to W eta is the space E eta, which is the same intersection, eta of n positive of U n. And for this guy, I do the definitions. Now, unless this eta is a coarse, this will be a point, and this will be 0 dimension. Because I will be intersecting guys that kill each other, essentially. So let me give you a very silly example. Okay, let's say we are in dimension 3. So I have 3, let's say we have 3 coarse. Let me do it for the linear to make my life simple. And let's say now eta, so this functional eta is a guy here. Now I have to put, as always, plus minus here, then, okay, so then here, this is first, second, and third guy. So here, we start with a plus, we move to a plus, and I still have a plus. Then when I move here, I have minus, minus, and then this has to be, oh, what a problem. Okay, now it should be good, because I move and I have a plus, minus, minus, and then I move and I have a plus, minus, plus, and now I'm happy moving all the way. So up here is minus, minus, plus, and up here is minus, 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 plus, plus, and up here is minus, plus, minus. Okay, so when I move here, I get, for a point here, for an n here, what is the unstable? Okay, and let's say, I have to say, let's say for this eta, plus and minus. So then I'm intersecting all the ends here. Now, for a guy here, the unstable is the second. Now, for a guy here, the unstable is E1 plus E2, so not much change. So when I intersect, I just get this E2. Down here, I have already that the unstable is E1. So when I intersect, I just already got nothing. Okay, and here, actually, I get E1 plus E3, and that was most likely to happen always. I move very close to this kernel, up and down, both sides, and I get E2 and the complementary of E2. So this intersection is 0. And this will happen no matter which eta you pick, okay? Unless you coincide exactly with one of these guys. So that's why you typically will get the 0 here, unless you are one of the guys, but still this statement here will hold whatever you take.
And you mean, so you use the word coarse when eta hits one of these guys?
Exactly.
Okay.
So whatever functional I'm using here, so I should put an eta here, then I have eta here, and I have eta here. And this is true for every eta. Now I pick eta equal to chi I. And when I pick eta to chi I, so if I don't pick eta either, so neither this nor that, then by definition of this and that, this will be 0, this will be 0, this will be 0, and I'm getting 0 equal to 0 plus 0. So there is no fun. Now I use it for this guy on the left. And by using it for this guy on the left, if this intersection over there were trivial, then I will get that this guy, which is 0, will be equal to this guy plus this guy. And this is not trivial, this doesn't matter, so I get 0 equal to positive plus something that's impossible.
So here, the second W eta shouldn't be the W eta.
This is for the rho, because this is rho, so this is for the rho.
Okay.
And this is for the alpha.
Okay.
And this is for the alpha. Yeah, so the first coordinate is telling you which dynamics is taking place.
Okay. Yes. Okay.
So this is telling me that whenever I consider this kernel, so this chi I am sorry, so this functional, this intersection is non-trivial. And this intersection being non-trivial tells you that you have to be proportional to this, to one of the guys. And then it's a matter of counting. Okay. And you get this. So I can relabel all the guys and just assume that chi I equals to the corresponding chi I. So this is the proof essentially using all the theory which developed. Let me give you the more geometric proof, which in this case is very suitable. The problem is that this proof fails when you try to do different actions. And that's why you have to develop the entropy, which is a much more robust argument. The second proof. Second proof does the following. Take, say, chi1. Okay? And remember what I said, which is a consequence of this picture, that when I take chi1, chi d here as a function from rd minus 1 into this space, which is all the x1, xd, such that sum of xi is 0, but this is an isomorphism. Which means that I'm pretty much like in these three-dimensional pictures I draw there. So we can pick n such that chi1 of n is positive and chi I of n is negative for every id from 1. I make my unstable one-dimensional. And my stable codimension 1. So for the linear, I have this E2 plus ED, and I have E1. Okay. Now I do the very same game I did with the yellow up there. So assume that the intersection with chi1 of n positive of EUN, let me emphasize, we are talking about the alpha dynamics here, that this is 0. Assume that this intersection is trivial. And well, there is some linear algebra we can discuss if you want, that if this is not happening, it's because one of the quarks has to be proportional to this chi1. Assume this is true. And now let me draw the dynamics. So I'm redrawing the linear dynamics, but now on the torus, so you pick a very small rectangle here. You build a box, which is just throwing stables from this square down here. And now I do pretty much, or I try to do pretty much the same picture above for the nonlinear dynamics. I take, so let me call n naught this guy. Okay. So it really doesn't matter who is stable or unstable. What does matter is that one is stable, the others are unstable. And I have this track. So I can always take the inverse. Now I take the unstable for the guy above. That may be 2-dimensional, maybe 1-dimensional, I have no idea, maybe 35 dimensions. But the unstable upstairs will go to the unstable downstairs, inside. While when I bring all the stables to this box, okay, for this I have to take some Pessin sets, so I have to do some Pessin theory here that I don't want to develop too much, but still I take a Pessin set of positive measure. When I take this Pessin set of positive measure, on all the points nearby these midpoints here x0, these tables are good size, so I just consider all the intersections with this base, and that's it. I'm drawing the picture now. So I take the union of stable manifold of some points x, where x, so some local manifold with x belonging to some set R x0. So Rx0 is contained in this unstable. Yeah, maybe the way I draw it, it should be unstable. It should be stable, doesn't matter. And when I'm saying as, I'm calling this N0, and I take this of this point x0. Okay? So that's what I mean. And now, since I'm taking all these points, as I said, so the points x are these intersection points, but these come from some points here on a Pessin set, and this Pessin set has positive measure. This set has positive measure. Okay? Now I will start playing. Remove this and not here, remove this and not here, and I'm playing with n. So this set now essentially depends a little bit with n, but it's still a set of positive measure. I will just take a couple of n's to play. And what's the role of the couple of n's? Now I need to do the things correctly. So I will intersect guys so that I okay. So I get, remember, I think I want to get zero measure upstairs or positive measure downstairs. But we will see in a minute how we do it. So I should have changed this. So let me make the following observation. So we have this fact, okay, following from the fact that mu of so lambda of h minus 1 of b, this is equal to mu of b for everybody else at b, and this is the fact that the push forward of mu is lambda, that's exactly the definition, but then this means that lambda of h inverse ha this is okay, what I'm doing. Then maybe I should put this guy here. Yeah, h goes up. I'm sorry. My bad. This is actually it is correct from the fact that I push mu down and I get lambda. Then when I apply to b equals to the set h of a, I get that lambda of h of a is equal to mu of H inverse of HA, and now I get the inequality the other way. Okay. But so this is larger than mu of A because A is contained in H inverse of H of A by definition. I'm right, no? Yes. So every point here I project it, I take the preimage and belongs to here. So that's the inequality. So that's inequality. Okay. So now I will manufacture this set A, which will have positive measure here, and will project into a set of zero measure. Now, how I make it project into a set of zero measure? Well, when I project a set like this, how this guy projects? So H of the union with X in R X of n of these guys. So H of the union is the union of H because forward image behave very good with respect to unions. So, well, you need to be onto, I guess, but the map is onto. So I get the union with X of H of X. Oops. Well, of X. And now H of the unstable is contained in the corresponding unstable. So this is contained in maybe some enlarged log this uniform continuity of H here happening of H of X. And actually, if X belongs to here, H of X will belong to the stable log n of this H of X naught. Okay, because when I apply H to this guy and H to this guy, I get the containment. Which means that I can remove this and have here some stable log of H of X naught.
What was this R, set R?
This set R is by definition, so we take P equals to P sub n Pessin set for alpha of n for some degree of continuity, and then we take some epsilon naught that depends on this choice of Pessin set Pn. Actually, both are pretty attached, which is the size of stables, and then Rx naught n is by definition this intersection the unstable manifold of size epsilon naught of X. And I should take, okay, now I really, let's move here. Let me do it here. So Rx naught n is Ws intersection the union with Y in the Pessin set intersection the epsilon naught ball of X naught of the unstable manifold log n for Y. Okay, so in the picture, I have my x naught here. I have my stable manifold log. I have some ball here, which is fixed. And then I take in all these unstables and I get, so these are the points y and these are the point x, which is down there. And well, the choice of this Pessin set is is so that so. By definition, this contains, I'm sorry, by definition of this set, when I do this union with x of the unstable log n of x, this contains this. I fully recover here because for every point here I project it and I recover it. So I'm assuming that this guy is positive. Okay, and as I said, I will argue by taking 3, 4, 5 x amount of n's, which actually no more than dimension minus 1 would be more than enough. If I do it correctly, 2 should be enough. So actually, let me assume that the point x naught is so that this is true for the 2 values or whatever amount of values of n. So if I'm going to for some epsilon very small, so that when I intersect all these guys, they still have positive measure. And then when I intersect all these guys, they will be containing the intersection of all these guys, which still will be a positive measure. And the contradiction comes about projecting it to the other side and getting 0 measure. Okay, so let's see then what's the choice of n's I need. And this comes essentially from here. So as I said, if I do it correctly with 2n, I already should see a 0 there. But in any event, I intersect finitely many of them, and I will see a 0. That's because this is subspace, and I need to drop dimensions. Okay? So if I cannot do it with finitely many, it's because I'm never getting to 0.
That's a matter of choosing n in different chambers.
Exactly. So if you take in each chamber, but actually, as I said here, so the correct choice is very close to the kernel and moving up and down. So that's pretty much the correct choice. So if you take a guy here and a guy here, it should suffice to the argument I'm going to do.
And you're saying actually 2 is sufficient?
Yeah, 2. So the claim, if you want, is there exist n1 and 2 such that EU n1 alpha and intersection EU n2 alpha is 0 with both, let's skip the notation eta of n1 positive, eta of n2 positive. So this is true unless eta is one of these quartz guys. So if you want, assuming this intersection is empty, you can pick just 2, making this emptiness. If I remember correctly, and this comes from moving very close to the thing. But since I don't want to really do this careful linear algebra, because I may be even wrong with that, there exist ni's. That's easy, much simpler to prove. From 1 up to 10 to the d, huge number, whatever, should be d minus 1. Maybe d, maybe 2 to the d. 10 to the d will do. You know, 10 to the 10 to the 10 to the d. One of these guys will do. So finitely many of them.
But at least 2, right?
Yeah, you need at least 2. That's for sure, because these are non-zero always. Well, unless your action is too silly, but that's easy to show. It cannot be too silly. Okay, so I fix this whatever finite amount, making this intersection 0 and keeping the unstable there. I hope this should do the job. Let me check. Yeah, I think what I'm saying is correct. I may need something extra about this and i's, we will see in a second what else I need. But as I said, this being a finite amount, I make assume that this is true for all these n's, and this, the intersection of all these guys has positive measure. Okay, so I call this guy R sub n, and then I get intersection in I of and I'm sorry, is the relative measure, of course. So it's about this point. And this is larger than positive. That's what I need. Okay, so I'm just taking x naught to be a density point for all these p and i's, and then make a choice of epsilon naught smaller than the epsilon naught of continuity of the Pessin set, and so that this is large, and then I get that. Okay, so far so good. Now the question is what happens when I start intersecting all these rectangles and anything else I need to intersect downstairs. Now I need to be a little bit careful of what I'm doing, and here will be the reason why I just need two of them. Because if I did things a little bit smarter, I only will need to get two of them. Let's try to be as smart as Kalinin-Katok and see what is the actual intersection that has to be 0 there. Okay, so let's do this three-dimensional picture again. So we have the third one here, we have the yellow guy here. This is plus and minus. Okay, wrong color. Okay, now. So this is the guy upstairs, which is not the guy downstairs. Or the other way around, I'm sorry, the other way around. Because I'm starting with the guy downstairs and I want to show it's a guy upstairs. Okay, so this is guy 1. And now I can take these two guys, N1 and 2, which belong to the very same Bell chamber upstairs, but these to different sides of the chi 1.
So wait, I thought chi 1 was one of the...
Well, but now I'm switching because I have to focus on the guy I'm trying to show it has to be proportional. So remember what we want to show. So we want to show chi 1 is proportional to a Lyapunov exponents for alpha.
I see. We're proving the lemma, I see.
Exactly, we are proving the lemma actually, yes. So since we try to show that this guy is proportional, then we pick this chi1 and we assume it's not proportional to any of the other guys. And that exactly means that I can stay in the same Bell chamber to both sides of this chi1.
So the white ones are the coarse Lyapunov exponents for the alpha.
Exactly. These are the ki mu, and this is the chi1 over here. And now I will do exactly what we were doing. So remember, we have these cages here. Let me draw them. Okay? The union of unstable log and h of x over stable log. Actually, even better, over h of this guy I just erased. That was Rx not of n, of which I only care that this is inside stable log. So, sorry, I can forget about here. So this is for rho, this is h of this for the same n, and I'm taking y here. Okay, so I have that this guy here contains h of the union with x in stable log for alpha n of x naught, actually intersected with this Rx naught n. This just emphasizes that this guy is inside here, of this W u log alpha n of x. So when I map these guys here, which is these boxes I was writing here, they belongs to here. Okay, and it's important I do a little bit more careful than there. There I mapped into, so I just put the stable manifold for rho here instead of putting h of the stable manifold. And it's actually better to put h of the stable manifold. Okay, so why is better to put h of the stable manifold? Because now I will take n1 and 2. I will intersect here for n1 and 2, and I will still keep positive measure for this guy, and I will show that this lies in a codimension 1 subspace. So what is the codimension 1 subspace? It should come from here. So h of this is contained in h of x plus this space es rho for n1, and when I do this is contained in h of x plus s rho n2. Okay, now since I'm choosing both guys in the same Bell chamber, actually this doesn't change at all. Okay, because the unstable for n1 and the unstable for n2 is the same guy, because I did not even change in the Bell chamber. So there is not much discussion happening here. So I don't care much. Even though I could do the swapping as well by whatever is in the blackboard below, but now what happens with these guys here? Okay, so this is contained here, this is contained here. As I said, this is equal to this, because when I switch from N1 to N2, this stable manifold doesn't change. So which means that is contained in the intersection of these two guys, which is h of x plus this space plus intersected with es rho n1. Okay, what is the intersection of these two spaces? So I made my choice. So okay, doesn't matter this because I'm just forget about the not. So I'm choosing n1 here. So chi1 is negative here, chi1 is positive here. Okay, and I'm choosing n1 and n0 and n2 so that the sign of, so my choices is chi1 of n1 is positive, chi1 of n2 is negative, and I'm really asking they to belong very close to this kernel. Okay, so what will imply essentially that the chi of nj does not change sign. Okay, so sign of chi I of n1 equals to the sign of chi I of n2 for every I different from 1. So for all the other Lyapunov exponent, there is no change of sign. So this means that ES rho n1 is the sum with chi I of n1 negative, so all the i's of these sets AI, while ES rho n2 is exactly the same, but removing the chi1. Okay, so, but adding the chi1, I'm sorry. So the guy above doesn't have the chi1, while the guy below has the chi1. So it's equal to ES rho n1 plus E1. So this intersection here is nothing but just the one with n1. Now I do the same for the unstables. And for the unstables, I will get exactly the opposite. So I interchange. And I get that the unstable for n2 is the sum, and for the n1 is the one for n2 plus the e1. Now, still, when I do the h of the unstable and the h of the unstable will be contained in the corresponding unstable. So when I do this here and this here, this is contained here and here. And since these guys will not change, because n1 and n2 belongs to the same Bell chamber, h of these guys will belong to the intersection. And so I get that h of the unstable manifold log alpha n1 is contained now in the intersection, which gives you the smaller one. It's contained in this h of x plus EU of n2. Okay, so now that we managed to do all this mess, all this discussion, let me finish with again the picture. So I have here the stable manifold log of x naught for ni alpha, which is the very same manifold. because I didn't change it. And then I have all these unstable manifolds. Here. And I'm mapping them for H by H. Now, the horizontal goes into this, which is the unstable, the stable for N1 rho over the point H of X naught. Now, each of the unstables go into these lines, which correspond to EU and to rho. Okay? Which means that when I map this picture, I get that the image belongs to H of X naught plus EU n2 rho plus ES n1 rho, which is actually the direct sum, which is the same as H of X naught plus the sum of EI I different from 1. So the A1 is not there. So I have one dimension less. And so what I got is that this guy has 0 Lebesgue measure because it lies in the codimension 1 space, while the measure mu of this guy is positive. So I have a set of positive measure landing into a set of 0 measure. And that's the contradiction. I'm sorry for the huge mess. And yeah, I got lost in the middle. I'm sure you got lost in the middle, but I hope that the final punch remains. So you have to be careful and take this N1 and N2 to both sides of the kernel that remain in the same Weil chamber for the nonlinear dynamics. And this is what you mapped into the linear. Okay, so this is the geometric picture versus the entropy argument.
So in this calculation that you made, that's on the board. That's not here. That's in the back.
Mm-hmm. Here.
So in this box. So are you using alpha-invariant for Lebesgue? Like, how do you know that H?
Oh, here.
Yes. How do you know that H of P is measurable?
Compact sets. This is a compact space. So this guy is a compact set. Because I'm using Pessin sets.
Right.
And this varies continuously, so this is a compact set. So okay. I just need to do it with compact set. Oh yeah. So yeah, and I wanted to mention as well that when we prove this statement, we never really proved this statement because there was one part of the argument, if you remember, that I didn't give you when proving the whole sum business, which was, I told you, was some linear algebra where you have to use linearity and play a lot of games. And this argument that you play upstairs is pretty much, this is the geometric version of this argument, where you start removing one by one the E1, the E2, the E3. So if you are to do this in the entropy situation, you still will do this type of argument. Okay, if you are not resonant, then you put to both sides of the equality, and then you will lose entropy instead of losing measure, but it's still this type of argument. So it's still some linear algebra type of argument, but it's the same type of argument.
So does the validity of the second geometric argument mean that the group is constant?
Here everything is abelian.
No, I know, but so this. Like you're really using the higher rank here.
Yeah, you're really using the higher rank. You really want to use the higher rank.
I'm asking, are we using the higher rank or that it's constant?
Or the Cartan, the Cartan property of the action. Yeah, well, for the geometric action, we are really using the Cartan property. And actually, one place where this fails very badly, this geometric property, but the entropy property case proof is still remain. If you have, for instance, chi1 equals to a chi2, where a is negative, then things start being a mess. Because when you do this argument here of intersections, we move from this side to this side, then yeah, the chi1 such type, but then there is a E2 direction that takes the role of E1. And then when you try to play this game, you are still getting a box. Simply one was written as this and the other was written as that, but you still get a box. And there are other configurations which make it even more complicated. So if it is not the truly Cartan situation, it really starts getting very messy, and you cannot do it in a lot of situations. Even worse, if you have some zero exponents already here, then it's really disaster. Because with zero exponent here, you don't recover a set of positive measure by doing this game of taking unstable from stable, because there is some zero exponent. And so the only thing you can try to do is take this horizontal as being a center stable, and then you bring the unstable from this center stable. That you could do, then the unstables will go to unstables, but the center stable, you don't know where it's going to go. And then you are again in problem. So, so you have all sorts of problems of this type if you are not in this fully Cartan situation. So you have to really play some argument here. But other than that, that's how it goes. So part of the game of really, that's how this started. So getting into this type of formula was exactly trying to give a proof of this without using the geometric approach. And in particular, being able to address the symplectic case, which is things of this type, or the zero exponent situation as well, where you can also deal with this business. Okay, but I think it's very, very late. So yeah, this Friday we will have no lectures, but on Monday we come back. So I will email in an event just to make sure everyone knows. Good. Sorry for the mess, the delay, and everything. Hope next Monday I do better.